speaker today, since I guess they're working together, or he mentioned, at least Leon mentioned to me, Thomas as a speaker. So I would like Leon to introduce him, please.
Sure. So thanks everybody for showing up. It's a good group. So Thomas did a master's and a bachelor's degree in Cambridge in the Department of Applied Mathematics and Theoretical Physics. And then for some mysterious reasons, he decided to come across the ocean to Canada. And he has just finished defending in January his PhD in applied math from Waterloo. I gave a talk at a meeting and he came up afterwards. I was talking about predicting things like sudden cardiac death. And he said, oh, well, this is what he's working on. And I was delighted to get a chance to meet him. And I was delighted when he decided to come to McGill. And he's working here with Gil Bubb and myself. And hopefully in some future talk, he'll tell us how to predict the risk of sudden cardiac death. Today is going to talk about distinguishing bifurcations and predicting bifurcations from time series. And I'll just point out that a couple of days ago, I looked up on his website things that he had done, and he gave a talk, a 3-minute talk on the topic of this conversation, a 3-minute talk summary of his thesis, which I thought was absolutely fantastic. So if anybody wants a 3-minute summary, you can turn off now and you can just go watch his thing on this film, or you can stick around to hear the talk. So thanks for coming and thanks for giving this talk.
Great, thanks for the very kind introduction, Leon. It's an absolute pleasure to be here with you all today, talking about my work. Yeah, I am going to be sticking around in Canada for quite a bit longer. I'm enjoying it a lot, and it's been a very welcoming place to do research. So thank you all for that. Okay, I'm just going to hide the images now so I can get to the slides. Okay, so today I'm going to be talking about detecting and distinguishing bifurcations from noisy time series data. And this is work that I did in collaboration with Chris Bao and Medora Nand. Chris is at the University of Waterloo, Medora is at the University of Guelph, and they were both my co-advisors whilst I was doing my PhD. Okay, we're talking about bifurcations. So let's just dive in with some motivation with pictures. So I've taken 4 examples from ecology of systems that we care about, but systems that also can exhibit bifurcations and therefore sudden changes in their dynamics. So on the left, we have lake eutrophication, which can occur as phosphorus levels increase beyond some threshold. We have the African wild dog, which is an example of an endangered species. We have fisheries and other populations that we as humans harvest that can suddenly collapse if we harvest them too much. And there are also predator-prey communities that can undergo sudden onset of oscillations. And so if we were to write down simple mathematical models for these systems based on the fundamental ecological principles, we would see that each of these possesses some bifurcation. And you can see there is a wide variety of bifurcations that occur. We've got the fold bifurcation, transcritical, and the Hopf. And so, you know, predicting these dynamics is very important because often the consequences of crossing a bifurcation are very severe. And there's a million-dollar question, are these bifurcations or their transitions predictable? And there has been hot scientific debate on this for the last decade, at least in the papers that I've been reading. And here is an example of a transition. This is a paleoclimatic transition, data received from ice cores, where authors Dacos et al., published in 2008, suggested that these transitions are in fact, to some extent, predictable through changes in statistical metrics, such as in this case, the AR1 coefficient that increases prior to this transition. So this question is the heart of what I'm going to be talking about today. So if you're interested in that, hang around. So part one of my talk, just a brief overview, I'm going to talk about early warning signals for critical transitions. This is basically detecting generic features of bifurcations in data using the phenomenon of critical slowing down. But importantly, I'm going to talk about the limitations of this approach, and that'll motivate the work that I was doing in my PhD, which was developing a specific type of early warning signal based on the power spectrum. And I'll show how we can use these early warning signals to distinguish between different bifurcations and provide an advanced warning compared to conventional approaches. And finally, after that, I'll dive into the black box of deep learning that has become so popular recently. And I'll ask the question, can neural networks help us detect and distinguish these bifurcations? And how do they compare to conventional approaches? Okay, so part one, early warning signals for critical transitions. This terminology became popular in a paper by Scheffer et al. About a decade ago called Early Warning Signals for Critical Transitions. And in this paper, they proposed that due to this phenomenon of critical slowing down, which occurs prior to local bifurcations, we can pick up on these generic features in time series data prior to the bifurcation. Now, critical slowing down can be visualized quite nicely using stability landscapes, which I have here. And the idea is that close to the bifurcation, the potential well of your system becomes shallower, and therefore you get this increase in recovery time following local perturbations. Of course, it's not ideal to have to perturb your system to work out if it's going to be near a bifurcation. In ecology, this is often infeasible. You can't just wipe out some part of an ecosystem to see how it recovers. But fortunately, Mother Nature is stochastic. As we know, there is inherent randomness in these systems. And this noise manifests itself as lots of micro perturbations to the system. And this results in an increase in variance and an increase in autocorrelation. To give you some intuition as to why this is the case, imagine that shallower landscape. If you've got some noise pushing your system around, it's going to travel further from equilibrium, resulting in an increase in variance. And the system is going to spend longer in the places that it does visit, which will result in an increase in memory and essentially an increase in autocorrelation, which is how correlated your system is at time t with the system at time t plus delta t. And that can be visualized using these difference equation maps. You'd see that closer to the bifurcation, you get your points lying more correlated along this line. Well, I should add that although this paper was quite recent, the mathematics for these concepts has been around for a very long time. For example, René Thom in the 70s publishing about catastrophe theory. The mathematics is essentially borrowed from these concepts. So since I believe I'm speaking to mostly a mathematical crowd, we can have a look at what's going on mathematically with a simple example. So here we have the normal form for the fold bifurcation, except I've just added some white noise term here, because these signals are actually only visible if you have a stochastic system. So we've got the normal form of the fold bifurcation, and then what I'm going to do is just substitute in this y variable, which will give us the residual dynamics about this equilibrium state, x is root mu. And then that'll give us this stochastic equation. And then I make this very significant assumption, you could say, where we drop the higher order terms. And this assumption is an okay assumption as long as your noise isn't too big. So this is valid for systems with small noise. And then when we drop those higher order terms, we get what's called an Ornstein-Uhlenbeck process. This was originally used to study Brownian motion. And this lambda term here is what's referred to as the dominant eigenvalue. It's the eigenvalue that goes to 0 as your bifurcation is approached. Note that as mu goes to 0, we reach the fold bifurcation, and that is the same thing as lambda going to 0. Now, this is a simple stochastic process. We can use techniques from the theory of stochastic methods. For example, this book by Gardiner from 1985. And we can compute analytical forms for the variance and the autocorrelation function. And you can see that as lambda goes to 0, indeed the variance does increase. It actually diverges. And the autocorrelation function, where tau is some lag time, does also go to 1, and it's an increasing function. So we see these metrics increase as the bifurcation is approached and can therefore be used as some sort of indication of this bifurcation approaching. So that's the general mathematical argument for using these metrics. But what about actually computing these early warning signals in action, or given some time series data? How do we actually work out if the variance is increasing or not? And so I'm going to illustrate this with Robert May's harvesting model. It's a simple model. It gives this bistability in the diagram here. And I should just mention, for those of you who haven't heard, sadly, Robert May passed away a couple of weeks ago. And if you're not familiar with his work, I highly recommend reading it. He was a pioneer in mathematical ecology, mathematical epidemiology, and also some chaos theory and many other things. So I highly recommend looking up his work. He's got lots of excellent papers in Nature. And so this is a very simple model for harvesting in a fish population. And you can see the bifurcation diagram here with its bistability, the potential landscape down here on the bottom left. And this is actually a simulation that I'm going to run. It's a movie. And we'll see that as the time series goes along, we can compute the variance and autocorrelation using this rolling window here. So we'll take a slice of the time series at some point in time, and as that time series moves along, we'll keep computing variance and autocorrelation. So I'm running the time series now. You can see the ball in the potential well shaking due to stochasticity. I'm going to increase the harvesting rate towards the fold bifurcation. And you can see that as time goes on, as we're approaching the bifurcation, the variance and the autocorrelation computed at lag 1 increase over time, and then the system transitions to the alternate state. So the idea is, if this bifurcation diagram was not known due to hidden complexities in the system, we might still be able to say something about an approaching bifurcation based on the statistics of variance and autocorrelation. That was, of course, a simple model, but there have been many examples or demonstrations of critical slowing down occurring in real empirical systems, such as microbial populations. In cardiology at McGill, it was shown how critical slowing down manifests itself prior to alternans, which is a period doubling bifurcation in cardiology. There's also paleoclimatic data, as I mentioned earlier. And finally, there is also a study that I was involved with at the University of Waterloo, where we showed critical slowing down in Twitter data prior to a sudden change in opinion regarding vaccinations. And so since I was an author on this paper, I'll just quickly go through what this study found. So this study was looking at critical dynamics, critical slowing down, in the context of disease dynamics and also population vaccinating behavior. Now, it's important to note that these two phenomena are very tightly coupled. One depends on the other. So in this time series here, what we have are the measles cases in California and also the vaccination coverage over time. And you'll see that in 2012, there were very few measles cases. But then, unfortunately, due to anti-vaccination movements and also this very considered low probability of getting measles, there was a reduction in the years over time of the vaccination coverage. And we know measles is a very infectious disease. So even at 92% vaccination coverage, you do get some wild measles outbreaks happening. The famous one was in 2015 in Disneyland, California. Now, in terms of that coupling, note how as the measles cases go up, so too does the vaccination coverage. In 2016, people started vaccinating their children again due to these measles outbreaks and due to presumably a perceived increase in possibility of infection. So we can write down simple mathematical models for these systems where the disease dynamics is coupled to the vaccination dynamics. And this is a very big research area that takes place in Chris Bowles' lab at the University of Waterloo. So I won't go into detail of this system for time reasons, but essentially what you do find in this system is that there is a bifurcation that occurs as perceived vaccination risk, the ratio of this to perceived infection risk, crosses some threshold here. So a healthy population would be here where, everyone is vaccinating their children, but, due to various reasons, if vaccination risk increases in people's minds, then you can get this transition to this state where lots of people aren't vaccinating and measles is an endemic disease. So this is a very bad transition to take place. And so in order to assess this, we want to look at people's opinion regarding vaccination, particularly parents' opinion on vaccinations. And so what a better place to look for opinions than Twitter, right? That's where everyone expresses their opinion, it seems. And so what we did is we scraped Twitter data from all of these years. And this is Twitter data related to the MMR vaccine or measles. And we take this data and we actually look for signatures of critical slowing down. I should add that this giant spike here, this shaded area, is the Disneyland measles outbreak. So that's when everyone was talking about measles on Twitter. And I should add as well, what we did is we classified the sentiment of these tweets as positive or pro or anti-vaccination using a machine learning classifier. And with the positive and the negative sentiment tweets, we actually found critical slowing down occurring in these tweets prior to the Disneyland measles outbreak. And then after the outbreak, we actually found the opposite of critical slowing down. We found these metrics to decrease back to their original levels. And our hypothesis of this paper is that this system actually approached this bifurcation here and then receded away from it due to this omega actually varying in time and the Disneyland measles outbreak giving a rise in this perceived infection risk and the critical slowing down occurring because of this bifurcation. Okay, so that was the study, and then the conclusions of the study are essentially, we could use Twitter data to inform policy or work out which populations are most susceptible to sudden anti-vaccination behavior and measles outbreaks. Okay, so we saw examples where critical slowing down was used in practice, but note that the examples I mentioned happened in retrospect, or they happened under very controlled experimental conditions. So if we want to use these early warning signals for prediction in real time, we need to take a hard look at the reliability of these signals. And we have to ask the question, does critical slowing down always imply an approaching critical transition? And vice versa, does an approaching critical transition always imply slowing down? So it's an interesting question. You might want to have a think about this, but I can certainly show you some opinions of certain authors after the 2009 Sheffer paper. Tipping Points, Early Warning and Wishful Thinking by Ditfelson, 1 year later. So their argument is that most critical transitions, at least from the climate perspective that they work in, are actually simply noise-induced and not by underlying changes and underlying drivers that would give rise to critical slowing down. So there is that possibility. There's a possibility that these transitions occur without warning in chaotic systems. When you have chaotic attractors, they can jump from one to the other. That doesn't have to involve critical slowing down. What about in ecological systems where the data is sparse and the time series are noisy? This can actually give rise to transitions without critical slowing down too. What about high dimensional systems? As Boerlich et al. Published, they showed that if you're measuring the wrong variable in a high dimensional system, that variable you're measuring doesn't necessarily give you warning indicators. And Kefi et al. Showed later that also you can get these signals prior to non-catastrophic transitions. For example, you might go through a smooth transcritical bifurcation, but you would still get early warning signals. So absolutely, early warning signals does not necessarily imply that you're approaching a critical transition. And briefly, these can be summarized as false positives, cases where you get slowing down and no transition due to either rising variance due to increase in external noise as opposed to inherently from noise within the system. You can have the smooth bifurcations, as I mentioned, and you could just by complete chance in a stationary system get increase in variance and autocorrelation. However, I'll add that in this age where we're getting more and more data, the chance of this happening and just having a random increase is less likely if you're analyzing a longer time series. The false negatives are the ones to watch out for. This is where we get a critical transition and no early warning signals. So these things just happen by complete surprise. So what are the times, what cases can this take place? We can have a critical transition that's not associated with a bifurcation, For example, the noise-induced transitions, as Ditlevson pointed out. We can also have abrupt changes in external drivers. For example, let's take the dinosaurs. Even if they had very sophisticated mathematical models for their population dynamics, they might not have predicted a meteorite because that is an external perturbation to their system. So, you know, that kind of thing might be a problem with the systems we study if it's an external change. Other problems that can arise are if we have sparse data, these signals are less consistent. We can have different types of noise, multiplicative noise, prior to a full bifurcation. That can be a problem because you have decreasing population abundance prior to the bifurcation. Therefore, you get a decreasing variance just because the size of the system has decreased. So you have to watch out for that too. As I mentioned, global bifurcations, spatial systems can be a problem too if you're only measuring in one location and the transition happens somewhere else. For example, this domino here, if you're only measuring that domino, you wouldn't necessarily know it's about to collapse. And also, this one's quite interesting. Higher order terms are generally neglected when talking about these early warning signals. And I think that's something that needs to be considered as well, could have some effect on the critical slowing down dynamics, because we're making linearization assumptions. And there's a good review of this by Dacos et al. In 2015. They do talk about these limitations. Okay, so I want to talk about some of the work that I was doing in spectral early warning signals, where I try and overcome some of these limitations that occur in the conventional early warning signals. In particular, how can we distinguish between these different bifurcations, given that they all get this critical slowing down phenomenon? So yeah, as I said, and as we know, local bifurcations come in a variety of different forms, and therefore a variety of different implied dynamics. And it'd be very useful as a policymaker or someone, you know, looking after some system to know what sort of transition might be approaching. And so as a graduate student, I set off on this project, and I'd just done a course in stochastic processes. So I immediately wanted to derive everything I possibly could about these bifurcations. And so I took the normal form for each bifurcation and just went through the process of analytically deriving how these early warning signals would actually behave. So just briefly, the mathematics is essentially you have the normal form. I note that this is in continuous time and discrete time because we can get different bifurcations when we consider discrete time. I use that linear approximation and assume small noise. You can solve these with integration, stochastic integration techniques, or recursion in the case of the discrete time system. And then with these equations, you can derive these statistical properties. Notice we're in multiple dimensions here because things like the Hopf bifurcation occur in a planar system. And you can compute the covariance matrix, the autocovariance matrix, which gives you things like the autocorrelation, and importantly, the power spectrum. That's what I want to focus on here. And this is derived using the Wiener-Kindchen theorem from the autocovariance matrix. So here are the analytical forms for the variance, the lag tau autocorrelation, and the power spectrum prior to every local codimension 1 bifurcation in continuous and discrete time. Notice how many of these bifurcations occur in the same group. So for example, you know, this autocorrelation function is the same for fold, transcritical, and pitchfork. Why is that? It's because of that linearization assumption, and these bifurcations, the normal forms actually become identical when you take that linearized form. So that's another reason to consider nonlinear terms in future work. Anyway, these linear terms, they're incredibly general expressions. So as you can imagine, I did actually end up finding papers, Riesenfeld, for example, from the 80s, where he actually derived the power spectrum for the discrete time systems. So some of these indicators are also in the literature. Okay, so I'm going to focus on the fold and the Hopf bifurcation. The important thing is to look at these analytical forms and see what they're telling us about the early warning signals prior to the bifurcation. So we've got the fold and the Hopf cases here. This is just the, what's this called again? The Argand plane, complex plane, where the eigenvalues move towards the imaginary axis as the bifurcation is approached. We know a Hopf bifurcation is due to complex conjugate eigenvalues. And take a look at how the autocorrelation function varies as the bifurcation is approached. For the fold bifurcation, it increases regardless of the lag time you use when measuring your autocorrelation. However, for the Hopf bifurcation, and this is not appreciated in the early warning signal community, you can actually get decreasing autocorrelation prior to the Hopf. And where's my mouse gone? Okay, so this occurs for cases when the lag time is roughly half the period of the underlying oscillations at the Hopf bifurcation. So this is something important to note, and even in some lags, you don't get any change. So Hopf bifurcations, you can get strange behavior in the autocorrelation. Perhaps more intuitively, we should look at the power spectrum. Prior to the fold bifurcation, we get this spectral reddening that is dominant by lower frequencies. And prior to the Hopf bifurcation, as you can imagine, we get these peaks at the underlying frequency that occurs at the Hopf bifurcation. And this actually occurs well before the Hopf bifurcation, which is a phenomenon known as stochastic resonance. You actually see those peaks in the power spectrum before the Hopf bifurcation arrives. So we get very different behavior in the power spectrum prior to these bifurcations. Why don't we use that as part of our early warning signal methodology? That's exactly what we did. So how do we harness this information in the power spectrum? Well, one idea we had is to fit the analytical forms that we derived to the measured power spectrum from the time series, and then use some measure of goodness of fit to say which power spectrum or which bifurcation this power spectrum corresponds to. So to do this, we used Akaiki's information criterion, which gives you a measure of how well your model fits the data. Sorry, it compares lots of different models to see how they fit the data. And if you're interested, it's computed using this. I note that it is proportional to the number of parameters you use. So if you throw more parameters into your model, it gets penalized for that. You actually want a low AIC score for your model to do well. What we end up using are the AIC weights, which are essentially the AIC scores, but normalized so they lie between 0 and 1, with 1 being a very good model fit and 0 being a forget about it fit. So I've got 3 examples here. These are time series that are run far from any bifurcation. We get this sort of white noise emerging. This one is near to a fold bifurcation, and this one is near to a Hopf bifurcation. And you can see, if you look at the AIC weights, if you can read this, it's quite small. But here, for example, the AIC weight for the fold is 1. Here, the AIC weight for the Hopf is 1. So really, these AIC weights are giving us a measure for a quantitative measure for the shape of the bifurcation, essentially.
And Thomas?
Yes.
I have a question. So, sorry, maybe you mentioned that, but what is the AIC standing for?
Oh, it's Akaiki's information criterion. And the paper here is by Hirotugu Akaiki, and it's a popular statistic in popular metric used in statistics to work out how well a model fits data.
Okay, thank you.
Okay, so we're using the AIC weights there, which are normalized between 0 and 1. I believe there are probably other good metrics for model fits too, but we went with this one. Okay, and one other thing I wanted to pick out from the power spectrum is the maximum power. So essentially the maximum value of this function, S of omega. And I want you to note that this maximum power from the analytical expressions, you can see that it asymptotically goes like 1 over d squared, where d is the distance to the bifurcation, distance measured in terms of the dominant eigenvalue. Whereas the variance goes like 1 over d, this reduced asymptotic behavior. And so S max actually increases, or it's more sensitive to changes in the bifurcation proximity, and therefore could be useful as an early warning signal that arises when variance is actually failing. It often happens where sigma squared is actually decreasing in time or changing. And so due to this stronger asymptotic behavior, S max is often a more reliable indicator than variance. So together we've got S max and the AIC weights to detect the bifurcation class. So I'll just show quickly an application with a model. I like this Ricker population model because it exhibits 2 bifurcations, a fold bifurcation when you increase F, which is the harvesting rate, and a period doubling bifurcation, which is in a way analogous to the Hopf bifurcation in discrete time, as the growth rate increases in this population. So we've got two bifurcations. Let's test the spectral early warning signals on this. So the exploitation scenario, the system goes for a fold bifurcation, and here I'm computing over a rolling window the metrics that I was speaking about that could warn us of the bifurcation. And here is the power spectrum measured at different times leading up to the bifurcation. So as you can see, this unimodal power spectrum arises with an increase in the maximum power, increases in, actually the variance honestly doesn't increase here. That's due to this being multiplicative noise, therefore diminishing the variance as this bifurcation is approached. This is the Kendall-Tau value, which gives a measure of whether this is an increasing trend or decreasing. So a Kendall-Tau of 1 is increasing, Kendall-Tau of -1 is decreasing, Kendall-Tau of 0, you can't say anything about it. So S-max does provide a better signal than variance. The autocorrelation increases as we'd expect, and the AIC weights, the AIC weight for the fold bifurcation is dominant throughout this time series, giving you a characteristic early warning signal that this is indeed the fold bifurcation that's approaching. We've also got the demographic change scenario. These almost look identical before you get to the bifurcation. And here you can see, though, the power spectrum is extremely different. Even well before the bifurcation, the brown one, for example, is T is 280. It's well before the bifurcation occurs. You can see this bimodal power spectrum telling you that this one is a Hopf bifurcation or a period doubling bifurcation approaching. And we get these indicators in S-max as well, very strong increase. The autocorrelation can decrease, as we saw earlier, depending on the lag time. And the AIC weights, you can see that W Hopf jumps up to 1 prior to the bifurcation occurring. So again, we get a characteristic early warning signal. This is, of course, a model simulation. So once we'd derived these, we thought we absolutely have to find some empirical data to test this on. And it's actually quite hard to find empirical data of exotic bifurcations. But as I was looking through the literature, I found this lovely paper by Gregor Fussman and colleagues, where they actually showed a Hopf bifurcation occurring in a live predator-prey system. So this study was conducted at Cornell, but Gregor Fussman is now at McGill and chair of the Department of Biology. So I'll just briefly summarize what they did. They set up a chemostat experiment with these species, Chlorella and Brachionis, that serve as prey and predator in the system. And they have nitrogen, which can come through this chemostat and provides nutrients to the system. I should note this delta is the dilution rate, and that is a control, that's essentially the bifurcation parameter for this system. It can change that dilution rate and therefore take the system into different states. And this model is parameterized to their experimental data. So what they found is that their model gives this wonderful bifurcation diagram where they see 2 Hopf bifurcations occurring, one at low dilution rates and one at high dilution rates. And then, amazingly, they took their experiments through different dilution rates, and this is real data here. This is what happened. They found that at low dilution rates, they get this equilibrium behavior. At intermediate dilution rates, they get these oscillations. And at high dilution rates, the system goes back into equilibrium behavior. So it really is demonstration of this Hopf bifurcation in the predator-prey system. So Gregor kindly lent me this data to test the spectral early warning signals that I've been developing. And so the first thing I did is I took this data and I computed the power spectrum for the time series of both the prey and the predator. And what you see here is the power spectrum in the oscillatory regime has, of course, 2 very prominent spikes at this frequency omega, approximately 1/3. And if you do the time period of that 2 pi divided by omega, you get approximately 20 days. And that is roughly what you see in this oscillatory regime. You have about a 20-day period. But what is amazing, for me at least, is that in these equilibrium regimes, when you compute the power spectrum, you also see these spikes at relatively low frequencies at about omega is 1/3, showing you that actually this period of oscillations is observable even in the data prior to the Hopf bifurcation. And this is in line with the spectral early warning signals that I've been talking about. The power spectrum does conform to that shape even before the bifurcation occurs. So if we actually take all the dilution rates that the experiments were conducted at and compute the early warning signals, we see that, I should add actually as well, that the Hopf bifurcation that occurs in the real system does actually occur slightly offset from the bifurcation diagram of the model. So the empirical bifurcation is occurring here and somewhere within this gray region here. And you can see that prior to each of these bifurcations, the variance and S max increase, and the AIC weight for the Hopf bifurcation is dominant prior to the bifurcation. So we do again see characteristic warning in this empirical predator-prey system. I want to add as well that I've written software in Python to compute these early warning signals. It's really quite basic to use once you get going with some Python, and I'm very happy to help anyone that would like to use it if they're interested in using early warning signals for some data that they have or a model that you have. And it's straightforward to download. It's on the Python package index, and it's called very imaginatively EWS tools for early warning signals. So feel free to take a look at that. It's on my GitHub account. Feel free to email me if you're interested in that. Okay, so part 3 of this talk, I want to look at deep learning and see how deep learning compares to these traditional metrics of variance and autocorrelation. So let's dive in. First, we should ask the question, why use deep learning? Everyone is using deep learning. Do we want to be just another one of these people that sticks deep learning in the piece of research that we do? And I want to justify why deep learning actually is quite a useful tool for this problem. So you might have heard of deep learning in the news or read about it in research papers, but it's essentially state of the art at the moment for anything related to pattern recognition. So recognizing images, video, speech, audio, or documents, you name it, it's become very good at doing that. And more recently, it's become good at classifying different time series. So for example, in electronic health records, I've seen a paper where the authors used a neural network, deep learning essentially, to distinguish between different ECG signals and therefore different diseases in a patient. Essentially what a cardiologist does, but automated and much faster. Another thing is a neural network is a universal function approximator. It can incorporate all these higher order terms that we dropped earlier when deriving early warning signals. So maybe they can do a little bit better by considering these terms that we dropped. And finally, these early warning signals I'm talking about, they're trends, they're changes in variance and autocorrelation. And so it's quite difficult to actually do statistical significance on that. Whereas the neural network outputs an absolute value. It gives you some sort of probability, or what it thinks is a probability of some transition occurring. And that's something you can work with for statistical significance. So we essentially frame this problem of detecting a bifurcation and classifying it as a classification problem typical in machine learning. We have some input, the input is our time series. We have some output, the output is just a vector of probabilities of each type of bifurcation occurring. And most importantly here, we have a null case where no bifurcation occurs. So if we have a system not approaching a bifurcation, we hope that our machine learning algorithm says, okay, yeah, probability of null is very high, 1. And this is a neural network. It's essentially just a function. Just think of it as a function. Now, one of the most important things about training a neural network is getting appropriate training data. And of course, we don't have a huge amount of ecological data. So we actually use simulation data. One other thing to note is we need diverse data. Okay, if you're making a classifier to distinguish between cats and dogs, and you just train your classifier on pictures of golden retrievers, it's going to have a hard time distinguishing Chihuahua, for example. So we need diverse data. We need data that covers all of our bases, essentially, all different types of system and bifurcations, essentially. So what is our algorithm for generating this training data? So what we do is we create a dynamical system where its coefficients are random variables. And the particular dynamical system we look at is that of a sum, essentially, of polynomials up to third order here. Where AI and BI, the coefficients are just drawn from a normal distribution. So we get these really wacky dynamical systems. And what do we do with them? Well, we want to find out if they have a bifurcation, right? So what we do is we simulate them until they reach an equilibrium. And then actually, if they don't reach an equilibrium, if they diverge, we just discard them to make our lives easier. We don't consider it a model we want our system to train on. So we find these loads of dynamical systems that go to equilibrium. Then we use this fantastic software called Auto. I'm sure many of you have heard of it. There's a load of authors that have contributed to it. And that essentially is bifurcation continuation software, which can take our model, move along the equilibrium branch until a bifurcation is reached, and tell us the location of that bifurcation and the type of bifurcation that is. So we do that to our system. And then once we have its bifurcation, we run a simulation with additive white noise and store that data. We store the simulation and the bifurcation type. And we also make sure that we're running null simulations where the parameters don't change. And then there's a little complication. The system can transition before the bifurcation point, and we don't want our neural network training on data that has already transitioned, right? So we use a change point detection algorithm to work out where that system transitions and only give the neural network the data prior to the transition. That's very important. And so we set this up as an algorithm, and fortunately we have some clusters at the University of Waterloo. So we managed to do this for 500,000 bifurcations. I said we needed a lot of data, and I wasn't joking. So we did this for a huge number of bifurcations, making sure that for each type of bifurcation, sorry, I didn't mention we only have 3 bifurcations here: fold, Hopf, transcritical, and null. So for each of those cases, we have an equal number of data points. So an equal number of models, sorry. And then we split that data into training, validation, and test, as you do with a machine learning algorithm. I'm running out of time a little bit, so I won't go into the neural network architecture, but it's essentially an out-of-the-box LSTM, long short-term memory network. They're the best ones for using for time series detection, classification, and we use CoRS, which is a Python package, and that runs on top of TensorFlow, which is a Google product for using neural networks. So that's the network architecture, and I'll just show you some examples. Currently, this is a neural network running on the residual data of those models that we generated. This is the test set data, and you can see that, yes, there are bifurcations, so variance and autocorrelation increase, but the deep learning algorithm is able to do better than this. It actually distinguishes the type of bifurcation. So here, blue is fold, you can see that increases before the bifurcation. Red is Hopf, that increases. Yellow is transcritical, and then the null time series is just, yeah, the DL says, okay, high chance that this is not a bifurcation approaching. So it does pretty well on the test set data. But note that this data is of the same distribution of the training data. We wanted to try something a bit more. So of course, let's try some models that were not included in the training set. So for example, we could go back to May's harvesting model or the Rosenweig-MacArthur model, which exhibits Hopf and transcritical. And note these are not the polynomial forms that we looked at before. See how the deep learning does. And this honestly blew my mind. It was able to generalize beyond that training set data to these more, well, still simple, but more complicated models. So you can see before the fold bifurcation here, the blue line goes up. Before the Hopf, well before the Hopf bifurcation, the classifier says, yeah, there's a Hopf bifurcation coming. That I think is due to that stochastic resonance formulation again. And the transcritical again works. So it's a sign that the neural network is generalizing beyond its polynomial dynamical systems. So talking about reliability, I'm just going to zoom through this. You can obviously and must talk about the reliability of a classifier. So you look at true positives and false positives. True positive, basically, it warns you and the transition happens. Great. False positive, it warns you and nothing happens. Okay, that's not so great. The worst thing is the false negative, transition happens and it doesn't give you a warning. But if the transition doesn't happen and there's no warning, that's called a true negative. And so this confusion matrix needs to be analyzed in order to test how good your classifier actually is. And one way of looking at it is the receiver operating characteristics curve, which plots the true positive rate by the false positive rate. If you have no predictive capacity, you're in the middle there. If you're a perfect classifier, you're up in the top left. And for a given discrimination threshold, you plot where your classifier comes on this graph. The discrimination threshold for the early warning signals is the Kendall-Tau value. The discrimination threshold for the machine learning is essentially its probability of a bifurcation occurring. And you do this for a bunch of different discrimination thresholds, and that gives you your ROC curve. And a metric to determine how good your classifier is the AUC score. It's the area under the curve, under this ROC curve. So an AUC of 1 is a perfect classifier, and an AUC of 0.5 is no better than random. And so we can do this for the early warning signals and the deep learning algorithm. And for a bunch of simulations of the fold bifurcation, we see that the deep learning has a better ROC curve. The transition, I should add, is happening at time 400. So I just wanted to see how it does 100 time points before the transition. It does okay, but it does much better, really quite well, prior to the fold bifurcation, and clearly much better than variance and autocorrelation. And I'll finish up by just saying we didn't just stick to models. Sorry, we didn't just stick to simple models. We moved to a very complicated climate model. We got in touch with some climate scientists from the University of Exeter, Chris Bolton and Tim Lenton. And they'd been doing some work with this very complicated, it's called FAMOUS circulation model, climate, ocean, atmosphere circulation model. And this model has been shown to give bistability in the Atlantic meridional overturning circulation. This is essentially the flow of current in the Atlantic Ocean, where warm water flows towards the North Pole on the shallower water, and cold water comes back very deep down. And essentially, this AMOC exhibits this bistability in this very complicated model. And Bolton et al. Showed that standard early warning signals, variance and autocorrelation, do exist prior to this fold bifurcation in this very complicated model. So now we looked at the deep learning algorithm on this very complicated model. And again, which blew my mind, is that the deep learning algorithm performs very well prior to the transition, which occurs at time 800. So variance and autocorrelation do work, but only much later. Actually, at time 500, the deep learning algorithm is already saying that yes, there is a bifurcation approaching. So to wrap up, we found that early warning signals due to critical slowing down are okay. They don't work in all cases, so they need to be used with caution. Spectral early warning signals using the power spectrum to compute early warning signals can improve the performance and give you some indication of what type of bifurcation is approaching. Deep learning outperforms early warning signals so far on the models that we've tested. We're yet to actually do it on real data, but that is of course coming next. And my final thoughts. Interpretability of neural networks is a massive thing at the moment. We have to ask the question, what is the neural network actually picking up on to give such good predictions? And therefore, as mathematicians, can we actually work out early warning signals that optimize the prediction? Because it's picking up on something, we just have to work out what it is. And I just don't think enough, or at least I haven't heard of enough work being done on the nonlinearities and constructing early warning signals based on that. So I asked applied scientists, do you have study systems where early warning signals could be tested or useful? And the mathematicians among you, do you work on techniques? I know there's many of you that are experts in bifurcation theory, stochastic processes, all these amazing things. Do you know of tools that could facilitate bifurcation detection, and have you thought about this? Thank you very much for your time, and I'm open to taking some questions now.
So thank you very much. Are there people who have questions?
I have a question.
Yeah.
Go ahead, Jacques.
Okay, so one of the issues in the pandemics is detecting changes in the effective reproduction rate in real time. So this can be thought of as an early warning problem. And if you look at different curves, you can interpret the difference between R effective but larger than 1 versus R effective less than 1 as sort of a separatrix that you want to be on one side or the other. Are your techniques adaptable to this situation, or have you ever taught in those?
Very interesting and timely question, thanks. Yeah, I guess it depends on how R0 is computed. Presumably that's coming from stochastic time series data of number of infectants.
Yeah, well, it's actual data in a population, and you have different groups or different regions, and there's some stochasticity in it. And when the number of cases is very small, it's essentially a stochastic process. But once you get to a sizable infected region, there's a deterministic plus a stochastic component. But in principle, you can, but there are techniques to compute the R effective from the data. Different techniques with smoothing and averaging and all of that. So you don't know any.
R0 bigger than 1 is a transition, right? A bifurcation.
Well, I actually R not big. Yeah, R not equals 1 is the transition point. So you can think of the process as basically approximated by a linear system, and you're trying to detect the threshold when R0, which is the exponent, which is actually you can think of it as the log of the exponential. So it's the exponent bigger than, well, I mean, it's like the Lyapunov exponent. Bigger than 1 is expanding, less than 1 is contracting.
Yeah, I definitely think there could be application in epidemiology, and I know some authors, in particular John Drake, who did look at early warning signals prior to disease outbreak.
Okay.
I don't know if you're familiar with that work, but it has been looked at.
Are there more questions?
I have a question.
Yeah, go, Anwar.
This is, by the way, a great talk. I really enjoyed it. Fantastic work. Thank you so much for the talk. So the thing is, I'm wondering if, I think you alluded to it, but I'm not 100% sure. You know, when you have a bistable switch, the stable manifold of the saddle is actually a key element of when the jump could happen. I mean, you don't have to wait until the fold in order to actually make the jump. This could happen much earlier. So my question is actually twofold. I mean, is this signal that you're detecting early, at least when it comes to the fold? I can't think of something similar when it comes to the Hopf. Is it due to the fact that maybe your system or the algorithm is somehow detecting these manifolds, like these changes or the shape of the manifold that allows these jumps to happen earlier than the fold itself? And if it's not, like, are you susceptible to actually failing to detect it early because of the fact that the jump could happen even earlier than the fold? Does that make sense? I don't know if
Yeah, it does make sense. That's a really good point. Yeah. So at least in the literature I've been reading, they're referred to as noise-induced transitions. I'm not sure if that's exactly what.
That's what I mean, exactly.
Yeah. So basically, before you get to the fold bifurcation, you know, you can get knocked out of your stable state purely by noise. And actually, in the examples I showed you, the transitions often did happen before the fold bifurcation arrived, but in most cases, the algorithm is still able to detect the change in the manifold, as you say, before the transition. So this gets difficult, and this needs to be experimented with. If you increase the noise, it gets harder to predict, right? Because you can jump earlier. But that's just the case. That's the way it is. You know, larger noise means harder predictability in these cases. But I think what you say is interesting about how changing manifolds happening very early could be what the machine learning algorithm is detecting. And maybe there could be work done mathematically as opposed to using black boxes in terms of actually taking advantage of those changing manifolds.
Thank you.
Thanks.
More questions?
Yeah, I could ask a question, Leon.
Sure.
Hi, Tom. So just a couple of points. First of all, on the auto being wonderful, I'm not sure if you're aware, but Dodel's actually in Montreal.
Oh, really?
Yeah, so that's where much of the code was written here. If you go back to the chemoset, where you had the power spectrum. Yeah, so where you have here in the initial steady state range, you see the power spectrum, you see the double spike.
Mm-hmm.
That will be because whenever you perturb away from the steady state, you're going to approach it again on the direction corresponding to the dominant characteristic value. And in this case, that's complex. So what you're detecting here with a single or a double spike, and they're all double, is the fact that the dominant characteristic value is always complex. So I'm not sure in this case, without your later stuff, that then doesn't really help very much to say if there's going to be a bifurcation or not. It's just telling you what the dynamics are like on the stable manifold.
I see, right. I suppose if you paired that with an increase in variance, would that then justify the assertion that it's going to be a Hopf instead of a fold?
Well, it would have to be a Hopf if the dominant one is complex.
Mm-hmm.
But I guess you need that increase in variance to say that it's coming.
Absolutely, yeah. Whereas knowing that it's complex is more about just knowing about the type of dynamics that you're in, and therefore the type of bifurcations that could exist.
Exactly.
That's a good point, thank you.
Any other comments or questions?
I have a question. Maybe it's a stupid point, but I'm a bit confused about your time versus order parameter approach. So basically, usually you look at like the order parameter as an axis, but in your case, usually your data is with time as an axis. So if like your order parameter doesn't change linearly with time, but does something different, quadratic or something more complicated, would that change your theory? Because like you're looking at autocorrelation and stuff like that.
Very good point, yeah. In all of the simulations that you've seen, the bifurcation parameter increases linearly. If it were to increase in some weird nonlinear fashion, that would change the scaling of the early warning signals. But I believe they would still be monotonically increasing as long as your bifurcation parameter was monotonically increasing towards the threshold.
Follow-up question. Can you, from the advance warning, can you predict the point at which the bifurcation happens?
No, but I have seen a paper that suggests it's possible if you're able to perturb your system beyond the linear regime and then monitor its recovery. Then you can actually start constructing a bifurcation diagram with that information. But if you're just given a time series approaching a bifurcation, there's technically no way to work out where that bifurcation is unless you have a perfect model, which we never do.
Okay, thank you very much.
Thanks.
Any more questions?
Yeah, so I had a quick question. Can you hear me?
Yeah, go ahead.
Sorry, I had a quick question which is actually related to the last one. So I was curious to know if you tried to do the prediction of the transition point with neural nets, maybe adding one more parameter to the outputs that might predict the transition time.
One more parameter. Yeah, okay, I get you. So
like not only the probability, but on an extra output parameter or something like that.
yeah, yeah. So the training data has all the bifurcation values. So technically you can train the algorithm giving it exactly where the bifurcation occurs and the time series prior to it. So that's an interesting point to, we could take it further and see if it's any good at doing that. I just don't know how, I mean, it's worth a try, but I would be very surprised if it was able to predict the bifurcation point exactly in where it is in time. But you know, who knows? I'm curious.
Thank you.
Thanks.
Another question?
I have a question, actually.
Hi, I'm
Hi, Gregor. Hi.
Thanks for analyzing these data in such an elegant way after all these years. It was a great talk. Since we are looking at this picture here, I was wondering, in these experiments, the parameter delta is not morphed over time towards the bifurcation point. Rather, these are different experimental runs that are kept steady at this dilution rate. So would it then be fair to say that the signal that you see even when the system is run at equilibrium dynamics kind of is a measure for the propensity of that system to potentially, with disturbance, run into a bifurcation, in this case, a Hopf bifurcation? So if you have a well-behaved equilibrium from a different ecological system, that there's no way at all that it will ever run into a bifurcation, you would not get that signal at all. Whereas in this system that is now run at delta equals 0.04, there's no bifurcation either, but it has system immanent this propensity to potentially run into a bifurcation. Is that a good reading of this signal that you see?
It's a very good point, thanks. Yeah, so you're right, these data, of course, are done at fixed dilution rates. So actually, if I go to the next slide, these increasing signals are not occurring through time, they're just occurring through changes in the dilution rate that were done in different experiments, presumably. And so this what we have here is more like a proof of concept that these changes in these signals do occur as you get closer to a bifurcation, but we haven't been able to show that it increases in time because the experiments weren't varying dilution rates in time. But I should add that when the spectral early warning signals are used, we need S max, or we need this value as well as the AIC weight classifiers, because it's not an increase in these that tells you the bifurcation is approaching. That's just saying whether you're in an oscillatory or a monotonic regime. So the two need to be combined. And also, yeah, we are limited in the fact that these time series are stationary at fixed dilution rates.
Thanks.
Thanks.
So Laurent has written a question. He says, Auto has so-called fold and hop functions that it evaluates to find bifurcation points. You may want to look at what those functions look like as inspiration for determining where the bifurcation occurs.
Okay.
So Lauren if we ever get back to McGill, Lauren is a few offices over. So
okay. I have to say, I've never actually looked at the underlying code for Auto. I've just, enjoyed its output and ability to detect bifurcations.
well, right. Okay. Well, if there's nothing burning, then perhaps we can thank Tom for really a very rich talk, huge number of potentialities, and really fascinating work. So we look forward to having you around in Montreal now.
It's a pleasure, thank you.
Okay, so thanks everybody for attending.